Well, hello again, Pre-Cal students. I hope that everything went well with section 1 of this new chapter. Again, let me know if you had any trouble with it. Otherwise, we're going to jump into section 2 of chapter 6 together today. We'll be looking at the property of dot products today. So this section explores the dot product of two vectors, which is a multiplication of two vectors that results in a scalar. Remember, a scalar is just a number. It doesn't have direction like a vector does. And so we're going to talk about what a dot product does, how we find them, and why it's useful in this lesson. So dot product of two vectors, u and v, happens when we do u dot v. And the way that we get at that, there's actually two major ways that we do. But the first one is we take the magnitude of u, we multiply it with the magnitude of v, and then we multiply that by the cosine of the angle that is formed when we place the two vectors in standard position. And we use the theta, the angle that results in an angle that is between 0 and 180 degrees. So we don't want an angle greater than 180. So we pick the one that's lesser than that. So in example 1, we see a quick example of doing this. So find u dot v if u is 6 and v is 4. So the magnitude of u is 6 and the magnitude of v is 4. And note here that we have the angle of v is at 30, the angle of u is at 150 at standard position. So we need the angle in between these two, which we know would just be 120, right? We subtract the 30 from the 150. So we take 6 times 4 times cosine of 120, and we get an answer of -12. And that would be the answer. That's the dot product of those two vectors. Notice that we started with vectors that have magnitude and direction, and the result in the end is just a scalar quantity. Now, to show you the other way that we can arrive at a dot product requires that we set up a diagram like this. So here again, we have our two vectors. We have u and we have v. We are splitting u into its components both in the x and y direction, u1 and u2, and the same thing for v, v1 and v2. Also note that v has an angle of theta sub v, and u has the angle of theta sub u. The angle in between the two of them is then theta. We also then, from all of this, note that the magnitude of u times the cosine of theta u is going to be this u1, and the same thing times the sine of theta u gives us the y component. And similarly, we can do this with v. V cosine theta v, v sine theta v, and we can get both the x and y components of the v vector. Okay, and so then we're just going to use here for u1, u2, where u1 equals the magnitude of u times cosine theta u, and u2 equals the magnitude of u times sine of theta u, and the same thing can be said for v. Now, with all of that, we can now make a proof here that the dot product in terms of the vector's components. So the crucial step is to note that when we wrote this originally, remember this before was cosine theta. Theta is the angle between the two vectors, u and v. Well, we can rewrite theta as theta u minus theta v, right? Theta u being the full angle from the x over to u, and then theta v being from x to v. And so the difference between them is going to be the amount of angle between the two vectors. Well, this, though, is the cosine difference identity, cosine of a difference of angles. So we can use that identity from your identity sheets that we did last chapter, and we can get this. Cosine theta u, cosine theta v, plus sine theta u, sine theta v. And now we can just substitute in the component parts. So notice we're just going to distribute this u and v into each of these parts, and we can arrange them however we want, right? We can multiply u times v, then cosine theta u, cosine theta v, or we can just rewrite it as the magnitude of u times cosine theta u, this part, and then the v times the cosine theta v. And then we have to also distribute all of this, right, to the other pair over here. And so that's what we have here. u sine theta u, v sine theta v. But we already saw from our previous slide that that can just become u1 v1 and u2 v2. So the dot product of u and v can also just be u1 v1 plus u2 v2. So we now have a second way to find dot product. If we know the x and y components of the vector, we just multiply the x's together and add them to the y components multiplied together. So this becomes really useful. Find each dot product given that P is 0, 3 and Q is 2, 4. Well, remember, the dot product is just we multiply the x components together, and then we add the multiplication of the y components together. So 0 times 2 plus 3 times 4. Well, the first becomes just 0, and 3 times 4 is 12. And we're done. Or how about this one? 2, 4 and negative 2, 1. Well, we multiply the x's together, 2 times negative 2. And we multiply the y's together, 4 times 1. So it's negative 4 plus 4 equals 0. So here's a few properties of dot products. U, V, and W are vectors, and K is just a scalar quantity. Okay, scalar, what we mean by that is just a constant. So U dot V also equals V dot U. Let me prove that quickly. So if U is U1, U2, and V is V1, V2, well, remember, when we multiply them together, it's just U1, V1 plus U2, V2. But by associative property with multiplication, we can reverse the order of those. We can do U1 times V1, or we can just say V1 times U1. We can do it either way. Well, then V1, U1, V2, 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 U2 is the same thing as saying V dot U. So in other words, U dot V is the same as V dot U. You can multiply in any order. They are the same thing on the dot product. Okay, the second property here is U dot V plus W can also be rewritten as U dot V plus U dot W. Thirdly, the any scalar like K being multiplied in ends up becoming just K times the U dot V or U dot K times V. So you multiply that K into either U or V and then do the dot product. Next, let's prove that U dot U is the magnitude of U squared. Well, if U is U1, U2, then to dot U with itself would just be U1 times U1 plus U2 times U2, which is U1 squared plus U2 squared, which, again, we could rewrite then as U1 squared plus U2 squared, and then take the square root and square it, which is just the magnitude of U squared. So U dot V equals the magnitude of U times the magnitude of V times the cosine of the angle in between the two vectors when they're in standard position. But that means we can also rewrite this as we can figure out, what's great about this is that we can figure out the angle between vectors. If we don't know the angle, we can figure that out by taking U dot V and dividing it by the magnitude of U times the magnitude of V, right? We're just taking this part and dividing it underneath this guy. And we can isolate then the theta. We take the arc cosine of that answer and get the angle measurement between two vectors. This is a really powerful tool. We can use the dot product to find the angle between two vectors through this. So find the angle between each pair of vectors. We're going to do an example of this. So P is 0, 3 and Q is 2, 4. So remember, cosine theta equals U dot V over the magnitude of U times the magnitude of V. All right, so P dot Q here. So we take the x's and we multiply those together, 0 times 2, and then we add that to the y's multiplied together, 3 times 4, and we get an answer of 12. Then we have to find the magnitude of U and V. In this case, it would be the magnitude of P and the magnitude of Q. Well, we get that by just squaring the first thing, adding the square of the second thing, and then taking the square root of all of that. So in the first case, it's just 3. In the second case, we do 2 squared plus 4 squared, and then take the square root of that. We get the square root of 20. So now we just put 12 over 3 square roots of 20, and we take the cosine. It's cosine theta of, it equals all of that. So 12 divided by 3 square roots of 20 is about 0.8944. And now we take the arc cosine of that value, and we get, if we're in degree measurement, 26.6. Remember, make sure your calculator is in degrees when we're doing these problems. But you should get an answer of 26.6 if you put that in your calculator, degrees. Find the angle between each pair of vectors. Okay, so here we have r and s, -2, 1, and 1, -3. So the first thing we need to do is remember this is our formula. Cosine theta equals u dot v over the magnitude of u times the magnitude of v. We find the dot product by doing -2 times 1 plus 1 times -3, and we get an answer of -5 there. Then we find the magnitude of r and the magnitude of s through that calculation. We then put the -5, the dot product, over the multiplication of square root of 5 times square root of 10. And so we get -5 over the square root of 50. When you do that, we should get -0.7071. And then we take the arc cosine of that, and we should get around 135 degrees. And yet here's one more example. See if you can do this on your own. If you need to, pause the video here and see if you can work this out. I'll give you just a second. Why don't you pause it here and then come right back. All right, so I'm assuming you actually paused it and that you tried to work this on your own. So the dot product you'll find first, you should get to an answer of 0. At this point, you could actually probably stop, because even if you find the magnitudes, it's going to be 0 over some number, which is still 0. So what's the arc cosine of 0? Well, you should remember then that's 90 degrees. So that's the angle between these two vectors. Okay, now at this point, it's good for me to let you in on a little secret here about dot products. So if you ever do a dot product and you get a positive value out of it, from that you will learn that the angle you get is always an acute angle. If the answer you get is a negative answer, then the angle that you're going to get is an obtuse angle. And if the answer that you get from a dot product is 0, that means that you have a right angle. It's 90 degrees between those two vectors. Now that's called orthogonal. When two vectors u and v are orthogonal, they are orthogonal if and only if the dot product between them is 0. What we're saying there is orthogonal, we mean that there's a right angle between the two vectors. Okay? So if the dot product is 0, you have a right angle between the two vectors, and that means that they are orthogonal to one another. That word orthogonal is an interesting one. We have some English words, right, where we use that ortho as the start of a word, like orthodontist, who helps make your teeth straight, or orthopedic, who works on bones to make sure they're straight, or your spine is straight, that kind of idea. Orthodox or orthodoxy is a word that we use to describe straight or right doctrine. So orthogonal is, in this case, a right angle, a right angle. And by right angle, in this case, we mean 90 degree, a right angle in that sense. I just want to show you there's a couple of places where the Greek comes in the Bible. Galatians 2:14 says, "But when I saw that they walked not uprightly according to the truth of the gospel." That word there, orthopedousin, is the word to walk straight or walk uprightly. Perhaps an even more famous one that happens in 2 Timothy 2:15, where it says, "Study to show yourself approved unto God, a workman that needeth not to be ashamed, rightly dividing the word of truth." There, orthotemunta comes from the Greek word orthotemeo, which means ortho meaning right or straight, and temeo means to cut. So rightly cutting, rightly dividing. There's a lot of people that believe that this is a word that Paul was associated with because he was a tent maker and he was used to having to cut things straight in order for the tents to work out properly. And so maybe this is a word from that trade. But he says he applies this to the word of God, saying that someone who handles the word rightly is one who rightly divides the word of truth for those who, for both for themselves as well as for those who they are teaching. Okay, so example 4 says vector v is v1, v2, is orthogonal to the vector u, which is -6, 4. Find the ratio of v2, v1, then find a general expression for all orthogonal vectors and verify that it is perpendicular to u. Okay, so what I just told you is something is orthogonal if the dot product of them equals 0. So we can use that to solve this backwards. So u dot v has to equal 0. Well, the u values we have is -6 and 4. So the -6 has to be multiplied by the v1 in the v vector, and then the 4 from u has to be multiplied by the v2. So we can just set this up as -6 times v1 plus 4 times v2 has to equal 0, which means that 4v2 has to equal 6v1, or in other words, v2 over v1 has to be in the ratio of 3 to 2. So we could make a constant here, k times the 2, 3, where 2k and 3k, where k is all real numbers. And then you can just show this to be the case. So -6 times 2k and plus 4 times 3k, well, you notice you get -12k plus 12k, which equals 0. So the ratio here is 3 to 2. Okay, so this is all important because it allows us to do something called vector projections. Now, the principle of orthogonal vectors becomes important when we're trying to project a vector onto another one orthogonally. Now, why would we want to be able to do this? So let me show you a diagram. Let's say that we had these two vectors. We had the vector u and we had vector v. But I want to not know the components of u and v along some like x, y coordinate plane. I want to know how much of u is going along vector v, and then how much of u is perpendicular to vector v. That's called a projection. So the amount of u that would be projected along v, we call that the projection of u along v. Projection vu, you see that there? That's a projection of u onto v. And then the part that's orthogonal or perpendicular to the vector would be then what's left of u. So the two formulas that you're going to learn here, and these you can again write on that sheet, maybe keep the sheet going from last chapter, or if you want to start a new one, that's fine. You don't have to memorize this. I'm fine with you having this with you. But the projection of u onto v is found by doing the dot product of u and v, then dividing that by the magnitude of v squared, and then we multiply that answer. Remember, that's going to be a scalar quantity, right? Because the magnitude is just a number. The dot product, remember, is just a number. So we take the dot product divided by the magnitude squared of v, and then we multiply that number into the v vector that we started with. And that's how we get the projection of v onto u. Then to find out what's left, the perpendicular component, all we do is we take the answer that we got from this and we subtract it from the u vector that we started with. Again, so that's the principle what we're doing. I think it's easiest to see this when we actually have an example. So let's do an example together. Example 5. Find the projection of u, which is -4, 3, onto v, 5, 2. Then find the orthogonal component w2 such that u equals projection of u onto v plus w2. All right. So again, we've got a little drawing here to kind of help you see this. So here is our vector v, and here is our vector u going up this direction. And we want to know how much of u is projected onto v and then what's left. Okay. Notice, first of all, that the projection of u onto v is first of all going to be notice in the opposite direction than v is going. But that's okay. We can still do this. We're just going to put in the numbers into the formula that we were given on the previous slide. So the projection of v onto u is the dot product of u and v divided by the magnitude of v squared and then multiplied by the vector v. So the dot product of these together would be, first of all, is -14, right? -4 times 5 would be -20, plus 3 times 2 is 6. So -20 plus 6 would be a -14. And then we just need to find the magnitude of v, which is this guy. So we're going to square the first one, which would be 25. We add it to the square of the second one, which would be 4. So 4 plus 25 is 29, and we take the square root of that. But then we square it, right? Which gives us back to the 29, because it's magnitude of v squared. So square root of 29 squared, we get 29. So that -14 over 29, we then multiply by the vector v, which is 5, 2, right here. And so we just have to distribute this guy into both of these values. And you get these crazy big fractions. Negative 70 over 29, comma, negative 28 over 29. Then if we want to find what's left, the W2, we just subtract that answer we got from U, from this original vector. So we take U right here, and we subtract off the answer that we just got. Notice it's subtracting it, so we're going to distribute that negative into both of these. Okay, don't forget to do that. And then when you solve all of that, when you get everything with a common denominator, we get, again, some pretty crazy fractions. But we can look to see if this seems reasonable. And again, I think it does. It looks kind of reasonable to what's going on the coordinate plane here. So another way to find projections is if you know the angle. And these happen probably more often than the previous case, especially in physics. So these are also important to know. But if you know the angle theta, then we can just make use of trigonomic identities and functions to just get to the projections of each of these things. So for example, cosine of theta here, cosine of theta is just W1 over U. And so we can, again, multiply this up and, or divide this over, again, rearrange it however we need depending on what part we don't have. So all we get here is that the magnitude of U times cosine theta gives me W1. And also the magnitude of U cosine theta, notice here we get negative of the projection, but should still work the same. So determine the downhill component of a 150-pound skier's weight that pulls the skier down a hill with a slope of 30 degrees. So again, we're just going to look at, we want to know the projection of his weight along this vector. Well, if we know this is a 30-degree angle and we've drawn a triangle here, then we know that this angle up here must be 60, right? Because we have a right angle down here. So 90 plus 30 is 120, so we're left with 60 degrees in 180 degrees total for a triangle on the interior of the angles. So we could just use here, we've got the weight, and we just need to know the horizontal component here. Well, the cosine function works really well, right? Cosine of theta. So if I bring out the triangle of this, and we know 150 pounds is the weight going downward, we have a 60-degree angle, and we have weight 1 is the projection that we need. We just know cosine of 60 equals adjacent over hypotenuse. Remember, this is the hypotenuse. This is the longest leg. So W1 over 150. And then we just multiply the 150 up here. So 150 times cosine of 60, and that's just 75 pounds. So he's going to be brought down the hill with 75 pounds of kind of force pushing him down the hill. Now, if we increase the skier's downhill trajectory here to, again, he's going from to a pretty steep decline here. Notice this is 56 degrees. Again, we can figure out what the angle theta is from that. This must be a 34-degree angle now here. But again, we just take the 150 times cosine of 34, and we now see that he's being propelled down the hill with 124.4 pounds of force. You also have problems like this in physics where you've got like something being pulled and there's a force that's acting upon something. The good thing to remember on these is that the amount of work done is defined as the product of the component of the force that is parallel to the object's motion and the distance the object moved. So the only way for work to be done is for actual motion to occur. So if I push my hands together and I just sit here, but neither of my hands move, no matter how much force I'm actually pushing together here, if they don't move, no work has been done. So in this case, where we've got a handle and it's being pulled at some angle, the only amount of force that's doing work is the force that moves the wagon in the direction that it's moving. Now, if I actually pick it upward as well, like I'm picking it off the ground as I'm moving it to the right, then that's also work that's being done. But in this case, if the wagon is rolling along the ground here, then the only work that's actually being done to this is the force in the direction of movement. So that means we need to do a projection of the force. If I'm pulling on this handle in this direction, I need the projection of the force down to here, where it's moving along the x-axis, the direction of the motion of the wagon. Again, these are all ways of describing that. So if I was going to then look at this example, it says, find the amount of work done by Rebecca as she moves a wagon 300 meters down the beach, pulling with 20 newtons of force on the handle, which is 35 degrees above the horizontal. Well, the force is that force that's along the x-axis. So we need to use the cosine trig function, cosine of theta, times the force that's being pulled, then times the distance that she travels. So it's 20 newtons of force times 300 meters of distance times that cosine of 35 degrees, because we can only use the x component of that force. When you do that, you get something like 4915 newton meters. Newton meter, also known as a joule. Again, this would be stuff that you would be doing in either physical science class or in physics. Before we close today, I wanted to just quickly mention a really, really great facet in this chapter. It's on page 301 and 302 of the book. And it talks a little bit about truth and mathematical proof. Sadly, there are many modern mathematicians who fail to see mathematics as the reflection of an underlying transcendent truth originating with God. If you guys remember way back at the very beginning of the year, I pointed out in another textbook, a secular textbook, that it said from the get-go that man is the creator of truth. We've created mathematics. It's our invention. It's our handiwork, all of the rest. And one of the things I just love about Bob Jones is they're so clear to point out that that's antithetical to a Christian worldview. Math exists because God made it, and we discover mathematical principles. We didn't invent them. We discover them. And one of the things that this little facet talks about is that there are things within mathematics that we can see are true, but we cannot prove to be true. And one of those examples comes from the Goldbach conjecture. So the conjecture was this, that all positive even integers greater than 2 can be expressed as the sum of 2 primes. Now, this has been inductively shown to be true, but it still has not been proven mathematically. This is a great reminder to us that truth is truth regardless of whether man is able to prove it. By the way, if you're able to prove this mathematically, there could be probably some fame and money involved in the mathematical world for you. But they've actually done some work with this on computers to show that all the way up to 4 times 10 to the 18th power, all positive even integers can be expressed as a sum of 2 primes. We can show that to be the case, but they haven't been able to prove it for infinite number of cases. And so that's why it's still not proven deductively, even if inductively it's been shown, that conjecture has been shown to be true up to 4 times 10 to the 18th power. Again, computers can chug through numbers and show these things to be inductively true, but that still doesn't show the mathematical proof as to why that is the case. So there are things like this in mathematics where we know them to be inductively true, but we have not shown them deductively to be true. We haven't provided formal proofs to prove that for infinite number of cases. So there are things that still extend beyond our ability to prove, but that doesn't make them untrue. Just as is the case with our relationship with the Lord, there is truth that goes beyond us. It doesn't mean that those things are irrational. They're just super rational, right? Beyond our ability to reason. But there are truths just like that, and math itself also has to admit that same reality. All right, well, your homework is page 299 and 300, doing numbers 2 through 30 and 44 through 50. Just do the evens. I didn't write that down there, but do the evens. I'm writing it in here now. Evens. But you should know that drill by now. I just have you guys do the evens in general. So do the evens for those. Hope that it goes well for you. Let me know if you have any questions. God bless you guys.